Welcome back. Now, we are going to look at important aspects of the pair potential, or what we call empirical, semi-empirical potential, based on some of the mathematical functions, as well as how we can look at very simple interaction between them. Before I go any further, I have to make you aware about the Born-Oppenheimer approximation, which is at the core again of the if you look at the semi-empirical potential functions. Because as you know from your basic chemistry that there is a nucleus of any atom, and then there are neutrons and protons in the nucleus, and then there are orbitals around those atoms, and those orbitals are filled by negatively charged electrons. So, proton has positive charge, neutron has no charge, and electrons have negatively charged. And there are shells in which these electrons will sit, and there are different kinds of numbers attached to each of these atoms, where you can look at the atomic number, then you can look at the spin numbers. There are a whole bunch of these 4 different coordinates that are given in order to define how the atom will be filled up. And this was based on the Bohr's first model of atomic atom, and then there were a lot of other development by Sommerfeld, who came up with much better understanding of Bohr's atomic model. So, if you look at those Bohr and Sommerfeld atomic models, or any one of the basic chemistry, then you know that there are electronic structures around the central nucleus. Now, if we are doing molecular dynamics simulation and we are putting atoms at particular location, we are essentially saying that they are points in a space. So, that what happens to all the electronic cloud around them? And that is where Born-Oppenheimer approximation comes into the field. Max Born and Oppenheimer, who came up with the idea that the electronic states of an atom couple adiabatically to the nuclei motion. So, you understand from the adiabatic process in thermodynamics, adiabatic processes are isentropic. So, there is no change in entropy in adiabatic process. That means, they are very tightly coupled. So, if you look at that kind of situation, then essentially center of mass of the atom represents the entire cloud. So, all the electronic states are being collapsed into the central nuclei of the atom, and that is where you can say these are the points. So, that is where the point charge model comes in, and so you can define that as everything is defined by the nucleus, and all the charges are also confined around the nucleus, and that is what is important for all potential function that you will see in terms of semi-empirical like Lennard-Jones, etc. And also there is another approximation that nucleus motion is far removed from the Heisenberg uncertainty principle lower bound. So, if you look at the Planck's constant, which defines the Heisenberg's parameters in terms of which is h hat over 2, and if you look at the multiplication of energy and the time, what you are looking at the frequency of motion of nuclear motion is far removed from Heisenberg uncertainty, and that allows us to then define the position and the momentum. As you know, Heisenberg uncertainty principle says that you can't have both. You can either define the position, and then you will have less accuracy in momentum, or if you define the momentum, which is with velocity and mass, then you cannot define the position. And so, if you want to get over again this uncertainty principle, then we are also looking at that we are far removed from that nuclear situation. So, this Born-Oppenheimer approximation with this length scale, which is far removed from nuclear, now we are able to say that yes, we can apply these semi-empirical positions. So, what we look at in experimental data for potential models, lots of experimental data goes into it. As I said, there is a lot of physics behind these interatomic potential function, because they are at the heart of what you can predict and how you can then compare those potential functions with the experimental data. So, let us look at some of the typical experiments that are conducted for constructing these semi-empirical potential function. So, we look at atom-atom scattering in the gas phase, which gives directly information about atom-atom potential. The scattering energy samples different region of the interaction depending on the energy of the of the colliding atoms. So, we are also looking at the scattering, which is Raman spectrum as well as IR spectrum. We are looking at gas phase data, example of the virial coefficients, how does the pressure changes and what is the real equation of state for them, and also some of the transport property like thermal expansion, bulk modulus over the potential. We also look at low temperature thermodynamic property, because we want to look at what is the lowest energy possible. So, we are looking at the material like most material from a solid at low temperature except helium, because if helium, it is very hard to get to low temperatures there. If the energy as a function of density is known, that gives fairly direct information about depth of the potential well. So, the reason we want to go to lowest temperature possible for that material, primarily because we want to sample the lowest part of the potential energy well, and also we want to look at then bulk modulus, how it grows with the temperature. So, we can find the curvature of that potential energy well. We also then want to look at other side of the potential function. So, if you think about potential function, you are essentially looking at different parts of that potential function and fitting the data to different parts. So, high pressure information, if you get that, that means you are putting a lot of pressure on the material and taking observation, and these are experimental observation, mind you. The samples, the interaction at shorter distance than at the lower pressure. So, what we are looking at, we are putting compression on the system and see how they behave. So, that is where we look at the repulsion part of the system. And then finally, thermodynamic data such as melting temperature and the critical point and triple point, this information is harder to use directly. However, we are looking at many body properties here, and it gives you some idea about cohesive energy. That means, if I am from the solid phase and if I am going away, then I am doing this cohesion energy, and that is what is important for us to understand in terms of physical data. So, all this physical data is essentially sampling different part of the semi empirical potential function. So, by using mathematical fitting of all this data, now you have very good understanding and parameters or coefficient that will go with the mathematical formula that you are using for the potential function and the force field around that. So, let me stop here, and we are now first going to look at non-bounded potential models from simplest model to very complex model, and then we will look at the bonded part, and then we will look at some VMDL to understand how different kinds of simulation lead to different understanding of the system. Thank you.